Thanks, Roberto. Thanks, everyone, for sticking around. Welcome back. Here in a slightly different context, so this is going to be a research talk. The title is Robust Spectral Clustering with Rank Statistics. So this concept of robustness hasn't really appeared in any of the mini courses, at least for statistical network analysis, but here we're going to see some relatively new and ongoing ideas in this direction. This talk is based on a paper that's available on arXiv. It's conditionally accepted at JMLR. It's together with my collaborator, Shanqi Yu, and my PhD student, Zhangquil Liao. Please, if you ever have questions, comments, feel free to interrupt me. Okay. So this is sort of a one-slide summary of much of the discussion in today's lecture, as well as in the mini course that we've been attending. So we're in this situation where we either encounter or construct a graph of interest G, right? We then convert that graph into some matrix representation, here just a binary 0-1 connectivity matrix telling us for which two nodes we have an edge between them. Then we compute some leading eigenvectors. This has the effect of doing dimensionality reduction, right? We've gone from an n by n matrix to an n by 2 matrix of leading eigenvectors. We plot the rows of that matrix in low-dimensional Euclidean space, right? And now we can apply a clustering algorithm like k-means or some expectation maximization algorithm to get colors or for cluster labels for each of our vectors here. And then if we want, we can go back to the original graph and identify vertices with the color corresponding to their low-dimensional embedding vector. Right? So this is sort of the overall pipeline. Now in these slides, I have a little bit of motivation for why we might consider this. That doesn't need to be sort of emphasized too much here, aside from the fact that, well, in practice, usually we observe a graph of this form where, it's difficult to visually make sense of it or even ask your computer to try to find a useful representation, when in reality, there is some underlying structure that we'd like to recover. For example, in this stochastic block model setting, we would like to recover the colors up to a permutation, given only knowledge for this uncolored graph. Jesus has mentioned applications, at least briefly, in neuroimaging, where the vertices or nodes in the graph correspond to brain regions, and edges correspond to structural or functional connections between them. In this talk, we're going to focus on block structure and block model settings, but there are other application areas and extensions that involve topics like manifold learning or trying to understand some low-dimensional structure beyond simply clusters or discrete centroids. So here is just a figure from a recent paper by my collaborator, Patrick Room-Delancey, published in NeurIPS, where he develops some of these ideas and looks at embeddings of adjacency matrices and their weighted variance, where we don't see cluster structure, but we do see some interesting low-dimensional, say, noisy surface or noisy curve segment, and perhaps there's some underlying meaning that we would like to derive from that, or perhaps we'd like to model this structure more generally. Right? Now, in the title I mentioned robustness. There's a vast and extensive literature on spectral embedding and spectral clustering, but if you look at it, comparatively few works address the concept of robustness. Here, what I mean by robustness will be heavy-tailed distributions for the edge weights, correspondingly having heterogeneous variance profiles for distributions that give rise to your data, or accounting for situations where there are actually entry-wise dependencies among our edge weights rather than having conditional independence. So there are certainly some works in this area. Two notable works in statistics are papers by Tony Tsai and his group and Aparna Sarkar. There's other work that appears in the IEEE literature, in the image recognition and computer vision literature, some algorithms and methods proposed for robust embedding and dimension reduction, but no sort of systematic development with a focus on theoretical guarantees necessarily. Okay, and that's sort of where this work fits into some of the existing literature. Okay, so our setting will essentially boil down to considering weighted stochastic block model graphs. Okay? So our observable matrix A has entries aij that are independent, but not necessarily identically distributed, where when node I belongs to block Gi and node j belongs to block Gj, then AI is drawn from the distribution with CDF capital F sub Gij. Right? For stochastic block models, these Fs are just Bernoulli distributions. In this talk, I'm going to consider absolutely continuous distributions here. What that's going to allow us to do is work with edge weights and avoid ties among our observed edge weights with probability 1. Okay, so now weighted stochastic block model where this block structure is represented in a collection of distributions here. So this is now just sort of a matrix representation for our distributions, right? For each pair, little k comma L, we have this choice, in particular, k times k plus 1 over 2 possible different distributions to work with here. Okay, and so an example would be, well, what if we just take a collection of normal distributions here with the same variance but with different means. On the left, we see an unordered plot of one adjacency matrix that we might observe, right? It's difficult to say anything just visually by looking at this, but now if we were to know or infer the block structure, then we would be able to order the rows and columns in such a way that it's revealed to us. And here it's revealed to us again in the difference of the expectations here. Okay? All right. So before we dig into the method and some of the theory, I want to show just a few examples of what low-dimensional embeddings can look like for different data-generating distributions. Okay? So we're going to consider different collections of Fs, so the CDFs, and we're just going to see what the embedding space looks like. Right? So let's start with maybe the simple case that we might be familiar with, so stochastic block models. Right? If we have just Bernoulli data in our adjacency matrix for a particular model, which I'm not going to specify here, but we can simulate and we can get a low-dimensional embedding that correctly distinguishes between the two blocks. Okay? This example is stylized. I have equal community sizes. And it's really the difference in the means reflected in the B matrix, right? The matrix of expected, the expectation matrix for adjacency that is leading to the structure here. So this is for a Bernoulli data embedding. Now let's change Bernoulli to something like beta, okay? So now what I've done is I've changed the distribution for the entries. I've kept the underlying mean structure the same, but because of the relationship between the parameters governing mean and variance in the beta distribution, what that leads to actually is a reduction in the variances, keeping the means the same based on these parameters. And we see the point cloud actually shrinking in a little bit, right? Notice if we go back, we see a little bit of, let's say, more concentration or a tighter clusters for the beta distribution here, okay? Now let's think about Poisson keeping the underlying expectation matrix fixed, but we know Poisson has mean and variance relationship. That's going to give us this embedding where we now see a little bit more variability in the embedding space, right? These point clouds are now dispersed a little bit more, okay? We can keep doing this. We can say, well, what if we have Gaussian distributions, and now what if we toggle the means and the variances? So if we increase the variance for the distributions, that actually leads to different variability in embedding space, as we're seeing here, right? Our point clouds have spread out a bit more. If we now change the mean structure and separate the distributions more, then we suddenly get tighter cluster centroids, and we can sort of do this back and forth, back and forth. We can add a little bit more variability here. We can continue this for different mixtures of Gaussian distributions. Okay, now for these specific examples, we're starting to see that it's a little bit more difficult to perfectly distinguish left and right, right? Our eyeball clustering is no longer necessarily perfect.
Josh, can I understand?
Please.
You mean you've got the top two eigen
That's right. I'm plotting the eigenvectors here, always the top two. There's always block structure.
Point and that map, yeah.
Yep. Right. Great. Great question. Yeah, any other questions at this point? Okay. So now it continues to work for different mixtures of Gaussians. What about something a little more drastic? What if we introduce t distributions for each of the blocks, right? So t with 10 degrees of freedom, okay, this example still not too bad, but what if we become more and more heavy-tailed? Okay, suddenly here is our embedding for degrees of freedom 2, and if you want to go all the way to 1 degree of freedom, the eigenvectors are no longer visibly useful for clustering, at least in this point, right? They've degenerated in some sense for this embedding. So at a high level, this talk is about going from the left panels to the right panels. In other words, thinking about a situation where either we can do spectral embedding meaningfully or we cannot, and seeing if we can develop a method and some theoretical guarantees for a robust alternative. Perhaps you'll agree with me that if we observe these point clouds, that's a little bit more exciting than if we were to observe these, right? And I claim that the relationship between these is going to be described precisely through the method that we're going to introduce. Namely, a transformation of the original data will lead a robust eigenvector point cloud, whereas the original is no longer useful for clustering.
And we're not going to get anything if we go to like the top 3 eigenvectors.
Great question. In general, no. I mean, you can cook up some toy examples where yes, maybe you could, but in general, no. That's right. Yeah. Even finding top eigenvalues, even sort of looking for a gap and saying which one are the top, this is sort of a difficult question depending on how extreme the distributions are. Yeah, but that's a fair point. Please.
So this appears when asymptotic, right? The separation. So you are keeping the sample size the same for all distributions. If I increase the sample size for the t-distribution, wouldn't it separate as well?
Not necessarily. Nope. There are existing results that say if you have sufficiently heavy-tail data-generating distributions, you provably won't be able to cluster, and that's because we can quantify localization of the leading eigenvalues. Right? So, but that's an excellent question. Yeah, in the plots I showed, everything was held fixed. The only thing I changed was the distribution. In some cases, perhaps they would start to separate, but at least for moderate n, we already see a visual improvement here. Yeah, great question. Yeah. Okay, so our procedure for robust spectral clustering is actually quite simple and natural to state. We're going to take our adjacency matrix. So this is a symmetric matrix. We're assuming that all the upper triangular elements are distinct, right? Which holds with probability 1 for our assumption of absolutely continuous distributions. We're going to take each upper triangular element aij, and we are going to construct a new matrix called R tilde A, whose entries are the rank of the adjacency element aij among all other upper triangular elements, divided by the total number of such elements plus 1. So let's maybe look at a quick example here. So let's suppose A, I don't know, let's say 1, 300, and 5,000. It's symmetric. I'm going to ignore the diagonal here. We construct now what we're calling R tilde A. This is the pass to ranks transformation. We're going to take the upper triangular elements and we're going to rank them among all other upper triangular elements and then divide by the total number plus 1. Right? So now, well, let's see. We have 3 elements going from smallest, second largest, third largest. Smallest, second smallest, third smallest. And the rank of this would just be then 1/4, 2/4, and 3/4. Right? So we've gone from, well, here this is just a special case, right? 3 by 3. We've gone to a situation where the entries of our matrix are now constrained to be between 0 and 1. Instruction. Okay? So this is a rank transform applied to the elements of our adjacency matrices. Now, in statistics and other settings, we see rank statistics appearing in robust problems involving hypothesis testing and elsewhere. Here, what we're going to do is take this adjacency, this matrix of normalized rank statistics, this R tilde A, and we're just going to proceed in the conventional spectral clustering paradigm. Meaning, given A, we compute R tilde A, then we're just going to compute a truncated eigendecomposition, right? Keeping the leading eigenvectors, call them U hat here, and then we're going to cluster the rows, right? And again, the rows of this eigenvector matrix give us an embedding in low-dimensional space. Right? Are there any questions at this point? I don't claim that there's anything difficult about what we're describing here, but there are some interesting new ideas that we're about to see and consequences of this transformation. Please. Yes. The intuition, which we'll see in a moment, is that taking ranks, even though it introduces some dependency among the entries, it still preserves the underlying block structure, and therefore there's hope that we can do some perturbation analysis to say that the leading eigenvectors are close to some ground truth that has block structure, and we'll see that in just a moment. Yeah, great question. Okay. All right. So our main contributions in this paper are the following. So we develop a collection of theoretical results quantifying how well the eigenvectors of this matrix R tilde A estimate some underlying ground truth eigenvectors. What is the ground truth? Well, here it's actually the matrix of expected rank statistics. Right? So again, A is a random matrix. We have this transformation of A, so R tilde A is still a random matrix. It has an expectation, right? And when we write it out, we see that it is a block-structured matrix up to a slight correction. So in our algorithm, we're ignoring the main diagonal elements of the input, and we're actually just assigning 0 here. Okay, but if we account for that 0, then indeed we have still block structure. And now B tilde is a matrix. It's a k by k matrix. And its entries are just the expected rank statistics when node I belongs to block Gi and node J belongs to block Gj. Okay? So I've just added a tilde onto the B that we're used to seeing for stochastic block model graphs. Right? Okay? So what we establish then is weak consistency in the sense that we are going to be able to recover the membership matrix, here denoted by this capital theta. Right? This is our membership matrix, which we called Z in a previous lecture. So we're going to recover this in a certain sense with high probability under certain signal-to-noise conditions. That's going to give us our weak form of consistency. Then we're going to upgrade that to what I call a node-specific strong consistency result. That says if you fix a node of interest, say the first node in your weighted adjacency matrix, then its embedding vector is going to be very close to the existing ground truth vector in the large graph limit with high probability and probability tending to 1. Right? Then finally, we're going to get an asymptotic normality result, which says that if we look at the difference of the embedding vectors, so if you take the embedding vector from your data, you subtract off the ground truth embedding vector up to a suitable alignment, that actually gives us a sequence of random vectors that converges in distribution to a normal, a multivariate normal, where the properties of that normal depend on the block that the vertex belonged to. okay? And so sort of at a very high level, these results demonstrate the statistical effectiveness and inferential validity of rank-based data transformations when paired with spectral techniques for dimension reduction. Okay. So let me just illustrate, because I think some of these ideas are really nice to see in picture form. So here, I'm going to consider a two-block setting. Each block-specific distribution is a contaminated normal, right? It's a normal distribution, but with some small probability. It's a normal with the same mean structure, but with a standard deviation that's 100 times larger than the original block, right? So and we're going to do exactly this pipeline. We're going to actually look at the embedding of A, and we're going to look at the embedding of R tilde A. Right? And for this simulation example, what we see is the properties of A in the left column compared to the properties of R tilde A in the right column. Right? So for A, if you look at the first few eigenvalues, well, they're pretty flat and pretty large. Here I've normalized by the size of the matrix. So I've divided the eigenvalues by n. I've also scaled the eigenvectors to have L2 norm n to the 1/2. Right, so we see some non-informative sort of eigenstructure here for A, whereas we see a precipitous decrease in the spectrum for R tilde A, which is indicating perhaps some low-rank structure. The first eigenvector is kind of all over the place for the adjacency matrix, same for the second eigenvector. Here, blue is the ground truth. Here is the blue corresponds to the underlying true block structure. And we see that unlike the adjacency matrix, for this R tilde matrix, the first eigenvector is very concentrated around this ground truth here. And if we look at the second eigenvector, we see actually in this case sort of perfect eyeball clustering. Right? This is sort of the perfect staircase step function that we would hope for in adjacency embedding. Right? So hopefully this illustrates that there is some value to considering this data transformation, and that it is robust in a sense that is visible and can be made quantitative. Right? So to develop the weak consistency results, we are going to turn to the Lane-Rinaldo 2015 paper, which establishes consistency of spectral clustering for stochastic block model in an unweighted setting. There, the choice of loss function is given by an overall relative error and a worst case relative error. These are two of the most classical loss functions that we see in spectral clustering literature. Right? This just looks at an input estimated membership matrix theta hat and says, okay, is this close to the underlying ground truth membership matrix capital theta, but modulo permutation, right? We're allowed to permute the columns. That doesn't actually change the cluster structure. And modulo or relative to the size of the blocks. So here, this overall relative error is normalizing by the total number of nodes. Here, if we want to look at worst case, we can penalize by looking at the largest such L0 norm difference over different blocks. Here, nk is the number of vertices in block K, and then taking a minimum over permutation matrices on the outside, right? So these loss expressions have this relationship, and what we would like to say is that in certain settings, they go to 0 with probability tending to 1 in the large data limit. Hence, that would establish a weak consistency clustering result. Right? Okay. We're going to use 1 plus epsilon approximate k-means clustering because this optimization problem has a direct relationship to the Davis-Gahan subspace theorem. It allows us to interface our perturbation results with these statistical consistency results, and we can actually compute this in polynomial time. So very, very convenient for analysis. Okay, we have bounds that are perhaps a little bit ugly, but the moral of the story is similar to what we've seen throughout the mini course, namely under some signal-to-noise conditions, here quantified through the kth leading eigenvalue of b tilde. So provided that this is not too small, and here provided we don't have too many blocks, then with high probability, this is a probability tending to 1 as n tends to infinity, we have upper bounds on both loss functions that we defined in the previous slide. And if we simplify this setting a little bit further to the special case when all the blocks have the same size and this smallest eigenvalue is order a constant, not depending on other parameters, then this simplifies into the following form. We have big OP bounds that look like roughly k squared times n to the negative 1 and roughly k cubed times n to the negative 1.
So this is all depending on lambda k, right?
That's right, lambda k of b tilde.
B tilde.
That's right.
Yeah. And is there an easy way to get a handle on this quantity?
Great question. In general, no, but in special cases, you can make concrete statements about it. Yes. In the traditional stochastic block model setting, we can work out explicitly, right, statements about the eigenvalues for the B matrix. Here, one additional subtlety is actually that the B tilde matrix depends on the sizes of the individual blocks.
There's a kind of complicated.
There's a complicated relationship, right, and I mean, in particular, it also depends on n, the number of nodes in our graph, and this is not the case for stochastic block model. But in a few slides, I'll show you a special case where we can analyze it. Yeah, that's a great question. Okay, we can translate the perturbation theory that gives us the weak consistency result to a more general statement without considering an algorithm where we're just looking at principal subspaces. Right? We can ask how well does the top k eigenspace of R tilde A approximate the true top k eigenspace in the expected ranks matrix. Right? And so we have just a high probability bound, which is that under the previous hypotheses, right, the difference in Frobenius norm of orthogonal projection matrices suitably normalized is not too large. Namely, it does not exceed some threshold with high probability. And here, again, this threshold depends on n. In this case, there's a dependence on the smallest block size, as well as we see lambda k b tilde in the denominator. Again, sort of a familiar concept to us. Right? If you're more familiar with some other results and sort of approaches in the study of linear models, then you may have encountered what's called the matrix trace correlation before. So given two full column rank matrices Y and Z, the matrix trace correlation is just defined as the trace of the product of their orthogonal projections divided by k and taking the square root. This gives us a quantity between 0 and 1. And so then a computation shows that this ratio of Frobenius norms going to 0 in probability is equivalent to saying that the matrix trace correlation converges to 1 in probability. So this is quantifying how well these subspaces align, how close they're getting to each other. In an overall sense, in an L2 sense, if you will, since we're working with the Frobenius norm. Okay. Now, what about individual nodes and the properties of their embedding vectors? We have a definition, which is that we're going to say that strong consistency holds individually for node I when there exists really a sequence of orthogonal transformations W, so that if we take U hat minus U W star, right, so this is just the matrix of leading eigenvectors from our data aligned to the matrix U of leading eigenvectors of our expectation. If this matrix, and now its ith row in L2 norm suitably scaled, is small, then we say that this is node-specific strong consistency. So we're not making a uniform statement. So like the 2 to infinity norm is a max over all rows. Here we're saying just fix a row of interest. We can ask about the properties of it specifically. And we're scaling here by this quantity because the entries of U can themselves go to 0. And without this scaling, then we would have potentially a trivial statement that doesn't actually guarantee any form of consistency. So a special case of a more general result says that in the case when we have a block model, when there is a kth smallest eigenvalue of b tilde that does not depend on the other model parameters, and all block sizes are of the same size, meaning their order n over k, then we have, for any fixed row I, we have a bound on this expression, and indeed it actually goes to 0 with probability approaching 1. So this bound is weaker than saying that the max of all rows goes to 0 with high probability, but it's stronger than the previous result, where with the Frobenius norm we couldn't control the behavior of any one individual node or its embedding vector. Okay. I also promised an asymptotic normality result. The idea is that we again have this difference of matrices of eigenvectors, right? U hat minus U W star. In fact, here W star is the solution to the orthogonal Procrustes problem in the Frobenius norm, which appeared as an exercise in the lecture notes from this morning. So we have a handle on what this is. We do have to, unfortunately, introduce an additional orthogonal transformation to align this point cloud. The reasons are sort of a bit technical, but it is needed. So what we then say is that for this result, if you take, say, the first node of interest, if you take its embedding vector, if you center, scale, and reorient that random vector, then that is converging in distribution to a multivariate Gaussian. And the covariance depends on the block that your node belongs to. So this is a statement about this vector, or really sequence of vectors, conditioned on vertex I belonging to block little k. And that distribution is multivariate Gaussian with mean 0, and a covariance matrix that we actually can say something about. It's related to these quantities up here. So namely, it's reflecting properties of the membership matrix. It's also reflecting properties of the matrix of expected ranks, expected normalized ranks. Okay, so let me make a few technical remarks about how we get these results and what we need to do so. At a very high level, it turns out that this matrix difference U hat minus UW star can be written in such a way that the effect of the noise is approximately linear on this difference. Now, I mean, in general, an additive perturbation of one matrix by another doesn't necessarily change the eigenvectors in a clear way, right? Certainly not guaranteed to be linear in general, but in this special case, through ultimately the fact that we have sufficient delocalization in the eigenvectors corresponding to the membership matrix, what we get is this approximate linear structure, and the leading order term we can show is of this form. Here, R tilde minus expected R tilde, this looks like an E matrix, right? Capital E of noise from this morning. So this is our noise matrix times a matrix. Well, here that depends on the model quantities, right? B tilde theta, there is an orthogonal matrix W here. Informally, if we're going to plot our embedding vectors, so the rows of U hat, and if we scale them, informally, if we focus on vectors corresponding to nodes in a particular block, then we see approximate normality in embedding space. Now, formally, asymptotic normality only holds for individual embeddings. It doesn't hold collectively for the entire point cloud. And in fact, it can't, because the eigenvectors are constrained by virtue of being orthonormal. Nevertheless, it's still approximately Gaussian in simulation. We have these expected ranks, which Roberto asked about briefly. Here, we can analyze them, but their form is quite difficult in general. We have to take into account expectations of random variable, here x distributed as the Lth distribution, and then take expectation of the CDF of the L prime block evaluated at x. We have expectation of a CDF of a different random variable, and so in some cases we can analyze this sort of explicitly and in some closed form, but in some model settings it can only be evaluated numerically. Right? In the stylized case, when we have a planted partition model, if we have k blocks all of the same size, and only two distributions, one for the diagonal blocks and one for the off-diagonal, then we can actually express lambda kb tilde very nicely. It has this form, either an expectation of a CDF minus 1/2, or just the probability that x12, which is distributed from the off-diagonal block, less than x11 distributed from the on-diagonal block minus 1/2. Right? So for SBMs, we're used to seeing P and Q, and in particular P minus Q captures discrepancy between the two Bernoulli distributions. Right? Here, this is capturing the discrepancy that the ranks C, actually, or the discrepancy that is encoding the sort of the signal structure if we passed a ranks. Here's just another plot illustrating an example when our robust approach visibly works and the spectral embedding procedure just using A, the raw data, does not work. This example is actually from a situation where the underlying structure is rank 2. I'm deliberately over-embedding. I think someone asked what happens for more eigenvectors. So in this example, even if we take more eigenvectors, well, we see extreme localization and no clear signal structure in the adjacency matrix, whereas in the embedding of the normalized ranks matrix, we see visible distinction, at least given to us by one eigenvector compared to the others. And then if we go further into the spectrum, we see no clear informative signal. Well, loosely speaking, it looks like perhaps these are, roughly Gaussian mean zero, but not useful for clustering or distinguishing the two blocks. Right?
Well, I mean, okay, are there like orange ones hidden under the blue ones? Because it looks like, I mean, if not,
Here we have perfect separation. Here they're on top of each other, right? Here they're on top, but we don't expect there to be signal because this isn't a rank 2 or approximately rank 2 setting. So the remaining eigenvectors are kind of just noise.
I just mean it almost looks like you cluster with like a circle and then a ring around it.
Here?
But I think you mean, yeah.
No, here there are points. I mean, points are plotted. No, that's right. That's right. There are red points under blue. Thank you. Thank you. Yeah. Okay. Just some brief discussion about the proof elements. So working with expected rank statistics, with the variance of pairs of rank statistics and the covariances of rank statistics is a little bit tedious and a little bit challenging, but it can be done. And that's sort of our approach to proving these results. We need control over this operator norm difference, right? The matrix of ranks minus its expectation. In this paper, we're using some combinatorial methods, essentially computing higher order moments and higher trace to get control. We're continuing to investigate that, and we have some follow-up work which should be able to improve some of the theory that we are talking about here. So we should be able to reduce some of the current, weaken some of the current assumptions. but fundamentally this is important for us. Weil's inequality for eigenvalues and the Davis-Gahan subspace theorem appear in our analysis and are used to prove these results. We use ideas from entry-wise and row-wise eigenvector perturbation analysis. That's what lets us establish the node-specific strong consistency result. Okay? And sort of a fun added aspect of this work is that to get the asymptotic normality, we actually draw from some existing literature in the 1950s and 1960s on what are called simple linear rank statistics and their properties. So these were well studied by Chernoff, Savage, Hayek, and we are able to use those results together with our perturbation analysis to obtain the asymptotic normality of the embedding vector. For people who are familiar with rank statistics and their properties, sort of the distinction here is that we're not working directly with the rank statistics and looking at a linear transformation and normalizing. Instead, we're looking at the truncated eigenstructure of a matrix of rank statistics. Right? So that's an added layer of complication, but the claim is that in spite of that, we can still show that the behavior of the rank statistics is driving the statistical properties in this model and still gives us asymptotic normality in these settings. Okay. If you have any questions about these, I'd be happy to elaborate. Now, one question you could ask is, well, what about situations where both the adjacency matrix and the matrix of normalized rank statistics work? In other words, what if I simulate and my embedding of A looks pretty good, right? And I pass to ranks and it still looks pretty good. When might I prefer one to the other? And can we do such a comparison on theoretical grounds? So we have some partial results in this direction. So here for a simple two-block model where we have Gaussian distributions, what we can study is a ratio of asymptotic variances. These are asymptotic variances associated to the embedding vectors through the asymptotic normality results. Right? So I claimed we have an asymptotic normality result for ranks in this paper. That's going to give us this expression in the denominator. And I claim for this setting, we can also derive an analogous asymptotic normality result for the embedding vector, giving us then the numerator. Right? So this ratio of variances looks like what's called asymptotic relative efficiency in statistics. We can plot this quantity for different parameter choices in our model. So here the parameters are the means and the variances of these block-specific distributions. And so we can consider two situations. On the right, we're plotting trajectories for different choices of standard deviation in our original data. And on the left, we're plotting different choices of aspect ratio, which quantifies the relationship between the block-specific means. Okay? So this dashed line gives us the value 1. So for points in our parameter space on 1, that indicates that both methods are performing the same, right, in the sense of asymptotic relative efficiency. Above and below denotes when one is preferred to the other. So when we're above the black line here, this gives us, this tells us that our pass to ranks procedure should be preferred because in an asymptotic sense, there's less variability or less relative variability here, whereas the opposite is true if we're below. And for this regime, what we see is that these trajectories are sometimes above the black line and sometimes below the black line. I'm showing in this model setting that neither dominates. Right? There are some cases when using the adjacency is principled based on this definition of principled, and other situations where you would want to use ranks. And the idea fundamentally is how much does changing the expectation structures or changing the variability, how much does that change the rank statistics and how much information you lose from the rank statistics, right? So I mean, the ranks have this property of sort of collapsing or reducing down both means and variances when we get everything here, right? Even if our original data was, in general, real valued. When your original data has a lot of variability and noise, then it can be productive to pass to ranks. That's what we're seeing by these curves being above the dashed line. However, if you have a lot of separation in the means, then it's relatively easy to cluster just using the adjacency matrix. You actually lose some information if you pass to ranks, and that's why we would expect to see here that the curve falls below this dashed line for large values of mu. Okay, in the interest of time, I'm going to just skip one more example here, and I'll mention just briefly that we have a real data illustration in the paper. We have roughly 100 connectomes or brain graphs. These are graphs taken from different individuals where each node corresponds to a brain region, and edges represent essentially strength of connectivity. Here our edges are integer valued. And for this example, what we have is a notion of ground truth clustering. Right? Our neuroscience collaborators and colleagues have, for this data, gone in and looked at each vertex or node and assigned it as being either primarily gray or white brain matter, and classifying it as being either left or right hemisphere in the brain. So we have a notion of ground truth partition for this particular data set. Here's sort of a one-slide snapshot of the data description and findings. So all of the graphs are roughly on the same size, so roughly 1,200 vertices in each graph. If you look at the row sums, so that would give you weighted degree, also called vertex strength, those vary dramatically. And so for just first few of the graphs, I'm plotting box plots for the vertex strength. And we see here sort of considerable, I would say, like heavy-tailedness or heterogeneity in the sum of the vertex strengths, which is inherited through heterogeneous edge weights in the graph. When doing dimensional reduction, we have to specify a method of choosing the number of leading eigenvectors. Here we use an established method due to Zhu and Godsey. This is a profile likelihood-based approach for automatically selecting how many eigenvectors to keep. We apply this procedure on our data, and what we see actually is, interestingly, that method retains more leading eigenvectors from the adjacency matrix than for the matrix of normalized ranks. Right? So for every graph we observe, we analyze it both with the adjacency and the pass to ranks. Right? So we're going to get two different embeddings for it. In about 2/3 of the cases, more vectors are selected for the adjacency matrix than for the matrix of ranks. And when we compare how well the eigenvectors reflect the underlying ground truth through adjusted rand index, what we see is a higher adjusted rand index across the graphs, telling us that the clustering and embedding through our robust procedure is better reflecting the ground truth cluster structure than if we were just to use the adjacency matrix. So we're using fewer vectors, fewer eigenvectors, and doing a better job of recovering the ground truth eigenstructure. So this is encouraging, at least for a very preliminary data example. Just to wrap up, so I hope I've convinced you today that this is sort of a study of a simple, user-friendly approach to robust spectral embedding and clustering. I talked about 3 different types of results: weak consistency, node-specific, strong consistency, asymptotic normality. Our theory covers cases when both the adjacency and the normalized ranks matrix work. There are existing results in the literature that tell us certain cases when the adjacency provably fails, again, through eigenvector localization. We get these bounds through some perturbation analysis, through some careful bookkeeping. with rank statistics. In ongoing work, we are improving some of our error bounds, improving some of our high probability statements, investigating sort of sharp results for this treatment of rank statistics, sort of fundamental limits, if you will, for weighted settings where you use rank statistics. And there's more work that we're doing on real data as well. So with that, let me end here. Thanks.